Let me remind you where we are in studying digital communication systems. We have a continuous message signal x of t with a certain bandwidth b. The signal is applied to a sampling circuit under the control of a clock, which establishes the sampling rate f sub s to successfully reconstruct the original signal from the sampled signal. The Nyquist sampling theorem says that the minimum sampling frequency, or the minimum sampling rate, is twice the bandwidth of the message signal, twice the highest frequency in the message signal. This sampled signal is then applied to a quantizer, which takes the sampled values and rounds them off to the nearest standard value as established by the number of bits used in the quantizer. The number of bits, and in this process of rounding off the sampled values, noise is induced into the sampled signal, which you can never get rid of that noise. It is going to be there forever. But we can limit the amount of noise by choosing appropriately the number of levels, which will correspond to the number of bits. So the number of bits is determined by the criteria goal for the signal to noise ratio in the quantized signal. So now we have the sampling rate in bits per second. The sampling rate in samples per second. The number of bits per sample, you multiply the two together, and you will get the bit rate for the digitized signal. The quantized signal is then turned into a binary number with a certain number of bits, and it is now a binary signal, which is a string of ones and zeros, which proceed at a certain bit rate, number of bits per second. Now this string of ones and zeros we are going to consider as a random signal, and since it's a random signal, we have to take a bit of a side road, a detour, to discuss how to find the bandwidth of this digital signal. And in order to do that, I've got to speak a bit about random signals and autocorrelation and power spectral density. Okay, a binary signal is a random string of ones and zeros, and since it's random, it can only be described by its statistical properties. We can't write an equation for this binary signal. We can only describe it through its statistical properties. And one tool to discuss the statistical properties of a random signal is called the autocorrelation function. The autocorrelation function is denoted by the letter R. Subscript X tells us this is the autocorrelation of the function of time x of t. It is a function of tau, which is a time shift variable. To find the autocorrelation of a random signal x of t, we take the random signal, multiply it by a time-shifted version of the random signal, and then this integral process finds the time average. So we're multiplying the signal by a time-shifted version of the signal and then finding the time average. And it turns out that the statistical and properties of the and frequency information in the random signal is also embedded into this autocorrelation function. By the way, autocorrelation, auto is for self, means self, and to correlate something is to compare it with something or to relate it to something. So we are using this function to relate a signal to itself. The autocorrelation is a function of time shift tau. Tau is the amount of time shift. You complete this integral, and which is essentially a time average, and integrate through with respect to t, and we will have a function of tau. The integral performs a time average, integrating with respect to t, evaluates to a function of tau, and x of t minus tau is simply a time-shifted version of x of t. And you'll notice this equation is similar in form to the convolution integral, so it's not entirely unfamiliar. We can write the autocorrelation of x as a function of tau is equal to x of t times x of t minus tau, and then the bar across the top to indicate a time average. We can find the frequency content of this random signal x of t by taking the Fourier transform of the autocorrelation, and that will give us what is called the power spectral density of the random signal. To this point, we've been finding the spectrum of a signal by taking its Fourier transform. We've been finding the spectrum of a signal by taking its Fourier transform. The Fourier transform of a random signal is not clearly defined, but what is clearly defined is its autocorrelation function, and the Fourier transform of the autocorrelation function gives us a power spectral density. The regular Fourier transform of a time signal is an amplitude spectrum. This is a spectrum of the power in the signal, but we can still find the bandwidth information and some other frequency information from the power spectral density. While we're looking at this random signal, it perhaps will have an average value, a DC value that is simply found by taking the time average of the random signal. It will have an average power. We find that, as we always do in finding average power, we take the signal, square it, and then take the time average. And if a signal has a DC value, an average value, then we could square that average value, and that will give us the DC power in the signal. So consider a random signal with a DC component and a time varying component. So what's described here is a random signal x of t. So if we were to plot this signal, this is t, it would have a DC component. So I'm going to draw a dashed line. This would be its constant value. This is its average value. And then on top of this average value, it's got a time varying component. So it's a random signal that looks something like that. The time varying portion is x with a squiggle above it. Or is that a tilde? Anyway, that gives us the time varying portion. And the total signal is the sum of the DC component plus the time varying component. And for shorthand, we could call the time varying component the AC component. It has a 0 average value. It's not sinusoidal, but since we're already calling the constant part, the time independent part, we're calling DC, so the time dependent we'll call AC for shorthand. If we want to find the total power in this random signal, we square the signal and then take the time average. So I'm taking the signal, x bar plus x squiggle, and squaring that sum, and then going to take the time average. When we square this term in parentheses, we get x bar squared plus x bar times x with a squiggle plus x with a squiggle squared, and then we time average everything. The time averaging is an integral process that can be broken up into 3 terms. So the time average will be x bar squared time averaged plus x bar times x with a squiggle, and then we time average plus x with the squiggle squared and time averaged. Now this cross term, this center term, x bar is a constant. X with a squiggle is the AC, or the time varying component. It has a 0 mean value. So we're taking a constant and multiplying it by, or multiplying a signal that has a value, a zero mean. So the constant times the time varying signal also has a zero mean. So this is going to time average to 0. And we are left with the total power in the random signal is equal to x bar squared is a constant, so that is that's the DC power. That's the average value squared is the DC power, plus the time varying portion squared and then time averaged. That is the AC power. So so we have the DC power plus the AC power. And another, for random signals, another way to express the AC power is in the variance. You might remember variance from your statistics and probability class. If you take that would be sigma x squared. That describes how widely varying a random signal is. So this is the variance. Sigma x squared is the variance of the random signal and is the AC power in the random signal. So the total power is equal to the DC power plus the AC power. The autocorrelation function takes a random signal and compares that signal to itself, or relates that signal to itself, and to do so we compare values of the random signal at 2 points in time. So here is a random signal x of t. We can find the value of the random signal at time t1. It will have a certain value, and we can find the value of the random signal at a time t2. That will have a certain value. In time t1 and t2 are some distance apart, which is and that distance is given by the value of tau. Now, if this time difference tau is a small value, then if we're told the value of x at time t1, you might be able to guess with a certain reasonable accuracy the value of the random signal x at time t2. See, if tau was small, then you could guess pretty closely what the two values would be. But if the time value tau is large, then your ability to guess the value is going to be is not going to be as high. You wouldn't be expected to predict the value based on, and this is all depending upon how rapidly the random signal changes compared to the time value of the time shift tau. So this variation in the random signal is embedded, or it can be described by using the autocorrelation function. So to picture what the autocorrelation function does, here is a random signal. I've just sketched out a random signal, and then this is a time shifted version of the random signal. I've happened to have x of t plus tau, so this point here is shifted to the left. That corresponds to this point. This point shifted to the left corresponds to this point. So you can see that this is the same random signal that's been shifted, in this case, to the left. Now, to find the autocorrelation function, we multiply these two, the original function and its time-shifted function, the time-shifted version, point by point. And when you do that multiplication, you could get a trace that looks something like this. This is the product of the two. And now we want to find the time average of this signal. And it for this kind of signal, it might be kind of difficult to do, but we could use the integral that we've looked at before. We take a length of it, total length capital T, and then we find the time average, and then in the limit you let capital T go to infinity, and that would give you mathematically the time average of this thing. Okay. Now, presuming that you can mathematically work that out, if you work that out for all values of tau, work out the autocorrelation for all values of tau and plot the value you get from the time average as a function of tau, perhaps you would get a function that looks something like this. And this is what an autocorrelation function might look like. And it's got some properties that are always true of valid autocorrelation functions. The first property is that it has a maximum value at time shift tau equal to 0. So this is the tau axis. This is tau equals 0. And the autocorrelation will have a maximum value at that time. It will never get higher in value than whatever that value is. It will be less than, perhaps, but that will be its maximum. The second property is that it is symmetrical. It will have even symmetry. It's a real function. It has only a real part, doesn't have an imaginary part, but and it has symmetry, even symmetry. The next property is if you look at the autocorrelation at time shift tau equals 0, that would be x of t times x of t plus 0. So that's simply x of t squared and then time averaged. That is the total power, is the value of the autocorrelation at time tau equals 0. So that's the total power. So the autocorrelation has the total power information built into it. If this random signal has a periodic component, so if you had a periodic sine wave, let's say, and on top of that sine wave you have a random signal added to it, then its autocorrelation would also be periodic with the same period as the periodic component in the random signal. If the average value of the random signal x of t is not 0, if it's got a DC component and it has no periodic component, then if you look at the autocorrelation value as tau is large, that will give the DC power in the random signal. So the DC power is off as tau gets increasingly large. The DC power can also be read from the autocorrelation. It looks like in this case it's going to have a DC average power of 0, but it's possible that it could be something else. Okay, if it has no DC component and it has no periodic component, then the autocorrelation as tau gets large will always tail off to 0, and that's what this example looks like it's doing. But if the random signal did have a DC component, it would not tail off to 0. As tau gets large, it would tail off to be equal to the DC power. And using the result we worked out not too long ago, that the total power, this is the total power, is equal to the DC power plus the AC power. Using that relationship, then that's going to make the AC power equal to the total power minus the DC power. Okay, it's just 7th grade algebra. So and since we have the total power in the autocorrelation function and we have the DC power, we can take the difference and that would give us the AC power, which is also the variance of the random signal. Okay, now the last thing I want to point out about the autocorrelation is that the Fourier transform of the autocorrelation gives us the power spectral density, and this is the power spectral density. We can we can use that to find the frequency content of this random signal, its bandwidth, and other frequency information. And I will come back to this relationship later on when we talk about random signals in more detail. But I'm going to use this result in finding the power spectral density and thus the spectrum of the random binary signals. And that will be the topic of our next discussion.